Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about graphing exponential decay functions. So we talked about exponential growth. Now we're going to talk about exponential decay. And let's talk about the difference between exponential growth and exponential decay, both in terms of how it looks in a graph and also the function itself. So if you recall, the form for exponential growth was also y is equal to a times b to the x, which, by the way, is not the same as y is equal to a to the x times b to the x. So if you remember your order of operations, then you first take the value of b and you raise it to the power of x, and then you multiply it by a. So you don't multiply a and b together and then take it to the or raise it to the value of x. Again, you take b, raise it to the value of x, and then multiply it by a. So if you recall your order of operations, you have parentheses, exponents, multiplication, division, addition, and subtraction. We handle the order of operations in evaluating expressions or solving equations in this order. So parentheses, then exponents first, then multiplication, then division, addition, and subtraction. So again, y is equal to a times b to the x is not the same as y is equal to a to the x times b to the x, nor is it the same as y is equal to a b to the x. All right, so just a clarification in terms of your order of operations, make sure that you get that straight. And I'm going to remind you again that the form for exponential decay and the form for exponential growth are both the same. Now the difference between the two is that the value of b in the case of the exponential decay function is going to be between 0 and 1. The value for b in exponential growth is going to be greater than 1. So let's take an example, and I'm just going to go ahead and erase some of this stuff here. So exponential decay would look something like, and let's do this in blue since we have an exponential decay function. Y is equal to 1/2 to the x. So y is equal to 1/2 to the x is exponential decay, and y is equal to 3 to the x is an exponential growth function. So you see the value of b in this case is greater than 1, and the value of b in the case of the decay function is going to be between 0 and 1. So in both cases, a is going to be greater than 0 for exponential growth and decay. We say that a is greater than 0. But for the value of b, you see that it needs to be greater than 1 for growth and between 0 and 1 for decay. All right, well, if we graph the growth function, it's going to end up looking, if you recall, something like this. It's basically just a reflection over the y-axis for the growth function is what you get for the decay function. And why is that so? Well, let's think about it. As x increases in the decay function, as x increases and gets more and more positive, so let's say y is equal to 1/2 squared, this value becomes smaller and smaller. It becomes a smaller and smaller fraction. So y is equal to 1/4. If I say y is equal to 1/2 where x is equal to 3, then y now is equal to 1/8. So you can see as x gets bigger, the value of y is getting smaller and smaller. So as we go along the curve, as x gets greater and greater, the value of y gets smaller and smaller. Now what happens, so let's erase this, what happens when x gets smaller and smaller? What happens to y? All right, so when y is equal to a negative value, x is equal to a negative value, remember negative exponents just means take the reciprocal of the given value and raise it to the power that's associated with the given number. So if I have y is equal to 1/2 to the -2, the negative value just says take the reciprocal of 1/2 and then square it. So if I take the reciprocal of a fraction, now I end up with a number that's greater than 1. So I have y is equal to 2/1. Now when I take the reciprocal, I remove the negative sign for negative exponent, so it becomes y is equal to 2 squared, y is equal to 4. All right, now if I make x equal to negative 3, I have 1/2 to the negative third power. The negative sign just says take the reciprocal. It doesn't say apply a negative value to the outcome for y. So I take the reciprocal of 1/2. That's 2 over 1. Now I've taken the reciprocal of that value. I no longer need the negative sign as the exponent or part of the exponent, so it's y is equal to 2 over 1 to the third power, which is equal to 8. So you can see as the value of x becomes more and more negative in an exponential decay function, the value of y becomes greater and greater. Right? So the value of x becomes more and more negative, the value of y becomes greater and greater. Now this is just the opposite for the growth function, right? So as x in this case becomes greater and greater in a growth function, then y becomes greater and greater. And as x becomes more and more negative, right, I take the reciprocal of 3 over 1, so I say y is equal to 3 to the negative 2, then this becomes y is equal to 1/3 squared. So you can see as y becomes, or as x becomes more and more negative, the value of y becomes smaller and smaller for an exponential growth function. And the opposite is true for the decay function. As x becomes more and more negative, then y becomes larger and larger. All right, so in this case, the asymptote is the x-axis. So again, the asymptote is that value that the graph gets closer and closer to but never touches. Now again, I can move, and we'll talk about moving the graph up and down and to the left and to the right. So the asymptote is not always the x-axis, but in this case, where I have y is equal to ab to the x, y is equal to 3 to the x, y is equal to 1/2 to the x, the asymptote is going to be the x-axis. The domain in all cases is going to be all real numbers, because I can substitute any value in for x and get a real number result for y. All right. So again, I can substitute any value in for x and get a real number result for y. Remember, the issues that we have in finding a real number result is when we have a negative value taken to the nth root, or as a radicand an nth root that is even. So if I have even taken to the square root, or taken to the 4th root, or taken to the 6th root, then this value becomes an imaginary number. It's not a real number. The other issue is when we have 0 in the denominator. We can't have 0 in the denominator, so in functions where x produces a result that has 0 in the denominator, then we cannot say that that value of x is part of the domain. All right, so the domain, all values of x that lead us to a real number result for y. And in this case, for both exponential growth and decay, the domain is going to be all real numbers. All right, so let's talk about transformations of a exponential decay function. Well, it's going to be the same form as we had for exponential growth. So the value of h shifts the parent function horizontally by h units, and the value of k shifts the function vertically by k units. So h shifts the function horizontally by h units, k shifts the function vertically by k units. If a is between 0 and 1, then the growth function is stretched. If a is greater than 1, the growth function is compressed. So if you want more detail on stretching and compressing, please visit the exponential growth function lesson, and I go over why the graphs are stretched or compressed when a is between 0 and 1, and then when a is greater than 1. All right, so let's take 3 different exponential decay functions or curves. Let's graph each of them, and then let's see how they shift based on the transformations that are given within the function and based on what we just evaluated here. So h units shifts horizontally, k units shifts vertically. Right, so in the first case, we have no shift. This is basically our parent function of the two. In the second case, I'm shifting the graph to the right by 2 units. So remember, the form is y is equal to a times b to the x minus h plus k. And in this case, the value of h is going to be 2. Now, if I said x plus 2, then x is going to be a negative 2. And why is that? Because I'm rewriting this as a times b to the x minus a minus 2, which ends up being positive 2, plus k. Okay, so let's graph the first function y is equal to 1/2 to the x, and let's see what we get, and we're going to graph this in blue. So let's identify some points on the graph. And let's see what happens when we substitute in values, just a few values for x. So I'm going to take the value of x, I'm going to take it 0 as the value of x. 1/2 to the 0 is going to be 1. And let's do this in blue. So anything, your 0 exponent leads to a value of 1. And I say 1/2 to the 1, that gives me 1/2. 1/2 squared gives me 1/4. And then I take 1/2 to the negative 1. 1/2 to the negative 1 is going to be 2. So remember, I take the reciprocal to the 1, and that ends up being 2. So negative 1 ends up being 2. And then I take 1/2 to the negative 2, and that gives me 2 over 1 squared, which gives me 4. 1, 2, 3, 4. Graph looks something like this. And then I say 1/2 to the negative 3, and I get 8, positive 8 as my value. So we're going to be somewhere up here. So you can see my exponential decay function from y is equal to 1/2 to the x looks something like this. I'm going to go ahead and fill in the graph with that blue line. And again, in this case, the x-axis is the horizontal asymptote. So the value of y gets closer and closer to 0, but never gets to 0. So if you take a look at this function, if I substitute any value in for x, I'm always going to end up with a positive number result for y. And I'll never get to 0. I'll get closer and closer to 0 as x gets larger and larger. This fraction gets smaller and smaller. Okay, so let's erase this, and we're going to handle the red function. Y is equal to 1/2 x to the x minus 2, and let's see what happens when we start substituting in values for x. So I'm going to take, in this case, I'm going to take 2 as my first value of x. 2 as the first value of x gives me a result for the exponent of 0. So 1/2 to the 0 is 1. So when I plot 2, now I plot 1 here. Then I'm going to plot negative, actually I'm going to plot 0. Let's plot 0 for x. So 0x, I get negative 2. 1/2 to the negative 2 gives me 4. So at 0, I'm at 4. And then the last one, let's take a look at what negative 1 for x does. I have negative 1 for x, that leads me to negative 1 minus 2. It's minus 3. 1/2 to the minus 3 is equal to 2 over 1 cubed, which is equal to 8. All right, so now I'm about right here. And you can see that the graph essentially is just shifted from this first function, y is equal to 1/2 to the x, to y is equal to 1/2 to the x minus 2. I've just shifted the function to the right by 2 units. Okay, so here's my shift to the right by 2 units. So you can see that, in fact, this is holding true. My transformation model says that I'm shifting h units horizontally to the right, and that's exactly what's happened. I've shifted the decay function to the right by 2 units. All right, now let's take another example. Y is equal to 1/2 x plus 2. So now let's test a point. Let's test 0 for x. And if we test 0 for x, we get 1/2 to the 0 is equal to 1. 1 plus 2 is equal to 3. So at 0, my graph is at 3. All right, let's test a point, let's test a point 1 for x. 1/2 to the 1 is 1/2. 1/2 plus 2 is 2 and 1/2. So here I have 2 and 1/2. And let's test a point negative 1. So negative 1 gives me a result of 2 for this part of the function. So 1/2 to the negative 1 is the same as 2 over 1 to the 1, which is 2. 2 plus 2 is 4. So negative 1 gives me 4. And then finally, let's test 2. Negative 2. 1/2 to the negative 2 gives me 4. 4 plus 2 is 6. So I have 2, negative 2 to the 6 somewhere about right here. Okay, so now I've shifted my graph up 2 units. All right, and that holds true, again, if we take a look at the transformations plus k can see that I have +2 as a shift. Let me go ahead and graph that function. And you can see again that I've shifted the graph up 2. Okay, so let's move on. We're going to talk about one more part about exponential decay. And we have an exponential decay model. Now the exponential decay model is very similar to the exponential growth model with one exception. The exponential growth model is y is equal to a times 1 plus r to the t. So if you take a look for a second, you'll notice the difference. The difference between growth and decay is that in this case, I'm subtracting that percent decrease, or that rate of change. And in this case, I'm adding, in growth, I'm adding that rate of change. Right? The number of years, or t stays, the t value stays in the same place. Initial amount, ending amount, all the same. The only difference is in an exponential decay model, this sign is negative versus positive. Right, so let's take an example, and that example is going to be what happens to the value. And by the way, I talk to my students about really dumb mistakes, and a really dumb mistake is to buy a new car. That's just based on the value of the decrease of a car and how quickly it depreciates. So I'm going to say conservatively that a car depreciates at a rate of 10% per year. And honestly, once you drive a new car off the parking lot, you've already lost 10% of your value. And so how much will a new $30,000 car be worth after 10 years? Right, so I say here's my ending balance, that's y. So if you look back in the model from the prior slide, of y is equal to a times 1 minus r to the t. Okay? So y is the ending amount, a is the initial amount, that's $30,000, and then I multiply that by 1 times the rate of decrease in decimal form, which is going to be 10% or 0.10, and I'm taking that all to the 10th power because I have 10 years. Right, so I want you to break out your calculator, and I want you to find out what the answer is. I'm going to pause here for a second. You can pause as well, and then I'm going to come back to you with the answer. Okay, so let's remember as we go through working out this solution, let's remember what our order of operations is. Right, we have parentheses first, so let's take care of the parentheses. 1 minus 0.1 gives me 0.9. And now I'm going to raise that to the 10th power. 0.9 to the 10th power gives me approximately 0.349. 0.349, and I want you to, when you calculate this, you're going to keep the full value in your calculator. Don't estimate it like I'm doing. There's no need to simplify at this point or to round. Now I'm going to multiply 30,000 times this value because that's my next order of operation. I'm going to have parentheses, exponents, now multiplication. 30,000 times 0.349 leaves me with a value of $10,000, $10,460, approximately 35 cents. Right, so I've lost in 10 years, I've lost $20,000 in terms of the value of my car. So always not a good idea to buy a new car because it depreciates so rapidly, and the value of the car is not an asset where you're building value, you're decreasing in value. And the flip side of this is the exponential growth part, and that is if I were to buy a new car, remember $15,000 difference. If I buy a used car at $15,000, basically, you know, this is a couple years after the new car, the lifespan is going to be relatively similar, maybe a couple years short. But if I think about that growth of $15,000 over 10 years, what's happened to that money, right? Not only have I lost money on my investment, but I've also lost money on the possibility of future earnings off the $15,000 I would have saved and invested had I not purchased a new car and purchased a used car instead. So the difference between $30,000 and $15,000, $15,000 in savings and buying a new car. And if I assume that I can make about 5.5% net of inflation on that investment, and I take that to the 10th power, then you're going to get a fair amount of money. So let's, we're going to go back to growth functions real quick, and you're going to take that function since you already know how to figure it out, and you're going to find out what the value of that $15,000 is. I'll be back in just a second. Okay, you should have come up with a value of about $25,622.17. Right, so in that course of the 10 years, you could have invested that $15,000 and made $10,000. So not only did you lose money on your investment, but you lost, there was an opportunity cost of about $10,000 from investing in a new car. You could have used that money, right, to to invest in some other stock or some investment, and you could have gotten about $10,000 off of that investment over those 10 years. All right, that's it. I got a couple practice problems coming at you in the practice session of graphing exponential decay functions.